Hello, my name is Lewis Flynn, and in this chunklet, we're going to introduce some graph theory terminology and how it relates to the European Airlines network. Vertices in the network represent airports in the graph, while edges represent scheduled flights between two airports. There are a total of 412 vertices and about 2,900 edges. Some interesting questions when looking at the network are: can you get from any one airport to any other? Which airports are in the center? And is there an airport for which its removal would make air travel from some airport to another impossible? These questions tie to graph theory in terms of graph connectedness, vertex eccentricity, and cut vertices. Two vertices, U and V, are said to be connected if a graph G contains a UV path. And as defined in Chartrand and Zhang, a graph G is connected if every two vertices are connected. Therefore, if G is connected, there's one component. The eccentricity of a vertex is the distance between V and a vertex farthest from V and G. This can also be thought of as the longest, shortest path from V to any other vertex in the graph G. Graph vertices on the left are colored by their eccentricity from small to large, and color from blue to red. The smallest eccentricity value in the graph is 4, and there are 49 of these vertices. We call these vertices central vertices. The largest eccentricity value is 7. There are 3 of these vertices, and we call them peripheral vertices. On the left, we represent only the blue and the red vertices. Again, the blue are the center vertices, which means that they can reach any other airport within 4 steps. And the red are peripheral vertices, and they can reach any other airport within 7 steps. The graph radius is the smallest eccentricity value. In this case, the European Airlines network has a graph radius of 4. The graph diameter is the largest eccentricity value. Therefore, this graph has a graph diameter of 7. A vertex V in a connected graph G is considered a cut vertex if G minus V is disconnected. What this means is removing a particular vertex will then disconnect other vertices from the remaining part of the graph. On the right side, we can see located in blue and indicated as a cut vertex, because removing it will disconnect the 2 other vertices as indicated. Some applications of these concepts to the military in terms of connectedness are that we often seek to have a connected system where communication, information, or goods can reach all destinations. Conversely, there are some applications where we require isolation, where we would want disconnected graphs because the spread of information is not desired, like in the skiff. For eccentricity, we often think of this as an aviation planning perspective, where an airfield with a low eccentricity value is better than one with high eccentricity, particularly for medical evacuation, where you want to be able to reach the terminal areas as quickly as possible, or logistic flights to ensure that supplies get to the remote locations. Also, placing aviation assets in the center of the graph tends to reduce these additional fuel stops. A cut vertex makes us immediately think of network interdiction or an attack, and is the most obvious application for the military for determining these vertices. But we can also look at it from a defensive perspective and in determining our own network resilience or vulnerability. I hope you've enjoyed this chunklet, and the only reference for this is the textbook, A First Course in Graph Theory by Chartrand and Zhang.